Ultrasonic testing is a family of non-destructive testing techniques based in the propagation of ultrasonic waves in the object or material tested. In most common UT applications, very short ultrasonic pulse waves with center frequencies ranging from 0.1-15 MHz, and occasionally up to 50 MHz, are transmitted into materials to detect internal flaws or to characterize materials. A common example is ultrasonic thickness measurement, which tests the thickness of the test object, for example, to monitor pipework corrosion. Ultrasonic testing is often performed on steel and other metals and alloys, though it can also be used on concrete, wood and composites, albeit with less resolution. It is used in many industries including steel and aluminium construction, metallurgy, manufacturing, aerospace, automotive and other transportation sectors. History: on May 27, 1940, U.S. researcher Dr. Floyd Firestone of the University of Michigan applies for a U.S. invention patent for the first practical ultrasonic testing method. The patent is granted on April 21, 1942 as U.S. Patent No. 2,280,226, titled Flaw Detecting Device and Measuring Instrument. Extracts from the first two paragraphs of the patent for this entirely new non-destructive testing method succinctly describe the basics of such ultrasonic testing. My invention pertains to a device for detecting the presence of inhomogeneities of density or elasticity in materials. For instance, if a casting has a hole or a crack within it, my device allows the presence of the flaw to be detected and its position located, even though the flaw lies entirely within the casting and no portion of it extends out to the surface. The general principle of my device consists of sending high-frequency vibrations into the part to be inspected, and the determination of the time intervals of arrival of the direct and reflected vibrations at one or more stations on the surface of the part. James F. McNulty of Automation Industries, Incorporated, then, in El Segundo, California, an early improver of the many foibles and limits of this and other non-destructive testing methods, teaches in further detail on ultrasonic testing in his U.S. Patent 3,260,105 that OE basically ultrasonic testing is performed by applying to a piezoelectric crystal transducer periodic electrical pulses of ultrasonic frequency. The crystal vibrates at the ultrasonic frequency and is mechanically coupled to the surface of the specimen to be tested. This coupling may be effected by immersion of both the transducer and the specimen in a body of liquid or by axial contact through a thin film of liquid such as oil. The ultrasonic vibrations pass through the specimen and are reflected by any discontinuities which may be encountered. The echo pulses that are reflected are received by the same or by a different transducer and are converted into electrical signals which indicate the presence of the defect. How it works. In ultrasonic testing, an ultrasound transducer connected to a diagnostic machine is passed over the object being inspected. The transducer is typically separated from the test object by a couplant or by water, as in immersion testing. However, when ultrasonic testing is conducted with an electromagnetic acoustic transducer, the use of couplant is not required. There are two methods of receiving the ultrasound waveform: reflection and attenuation. In reflection mode, the transducer performs both the sending and the receiving of the pulsed waves as the sound is reflected back to the device. Reflected ultrasound comes from an interface, such as the back wall of the object or from an imperfection within the object. The diagnostic machine displays these results in the form of a signal with an amplitude representing the intensity of the reflection and the distance, representing the arrival time of the reflection. In attenuation mode, a transmitter sends ultrasound through one surface, and a separate receiver detects the amount that has reached it on another surface after traveling through the medium. Imperfections or other conditions in the space between the transmitter and receiver reduce the amount of sound transmitted, thus revealing their presence. Using the couplant increases the efficiency of the process by reducing the losses in the ultrasonic wave energy due to separation between the surfaces. Features: advantages: high penetrating power, which allows the detection of flaws deep in the part. High sensitivity, permitting the detection of extremely small flaws. Only one surface needs to be accessible. greater accuracy than other non-destructive methods in determining the depth of internal flaws and the thickness of parts with parallel surfaces. Some capability of estimating the size, orientation, shape and nature of defects. Non-hazardous to operations or to nearby personnel and has no effect on equipment and materials in the vicinity. Capable of portable or highly automated operation. Disadvantages: manual operation requires careful attention by experienced technicians. The transducers alert to both normal structure of some materials, tolerable anomalies of other specimens and to faults therein severe enough to compromise specimen integrity. These signals must be distinguished by a skilled technician, possibly, after follow-up with other non-destructive testing methods. Extensive technical knowledge is required for the development of inspection procedures. Parts that are rough, irregular in shape, very small or thin, or not homogeneous are difficult to inspect. Surface must be prepared by cleaning and removing loose scale, paint, etc., although paint that is properly bonded to a surface need not be removed. Couplants are needed to provide effective transfer of ultrasonic wave energy between transducers and parts being inspected unless a non-contact technique is used. Non-contact techniques include laser and electromagnetic acoustic transducers. Inspected items must be water-resistant, when using water-based couplants that do not contain rust inhibitors. Standards: International Organization for Standardization, ISO 7963, Non-Destructive Testing, Ultrasonic Testing, Specification for Calibration Block No. 2, ISO DIS 11666, Non-Destructive Testing of Welds, Ultrasonic Testing of Welded Joints, Acceptance Levels, ISO DIS 17640, Non-Destructive Testing of Welds, Ultrasonic Testing of Welded Joints, ISO 22825, Non-Destructive Testing of Welds, Ultrasonic Testing, Testing of Welds in austenitic steels and nickel-based alloys, European Committee for Standardization, EN 583, Non-Destructive Testing, Ultrasonic Examination, EN 1330-4, Non-Destructive Testing. Terminology, Part 4, Terms used in ultrasonic testing, EN 1712, Non-Destructive Testing of Welds, Ultrasonic Testing of Welded Joints, Acceptance Levels, EN 1713, Non-Destructive Testing of Welds, Ultrasonic Testing, Characterization of Indications in Welds, EN 1714, Non-Destructive Testing of Welds, Ultrasonic Testing of Welded Joints, EN 12223, Non-Destructive Testing, Ultrasonic Examination, Specification for Calibration Block No. 1 is replaced by the EN ISO 2400-2012 Non-Destructive Testing, Ultrasonic Testing, Specification for Calibration Block No. 1, EN 12668-1, Non-Destructive Testing, Characterization and Verification of ultrasonic examination equipment. Part 1, Instruments, EN 12668-2, Non-Destructive Testing, Characterization and Verification of ultrasonic examination equipment. Part 2, Probes, EN 12668-3, Non-Destructive Testing, Characterization and Verification of ultrasonic examination equipment. Part 3, Combined Equipment, EN 12680, Founding, Ultrasonic Examination, EN 14127, Non-Destructive Testing, Ultrasonic Thickness Measurement, see also, Non-Contact Ultrasound, Phased Array Ultrasonics, Time of Flight Diffraction Ultrasonics, Time of Flight Ultrasonic Determination of 3D Elastic Constants, Internal Rotary Inspection System Ultrasonics for Tubes, EMAT Electromagnetic Acoustic Transducer, ART, References. Further reading. External links, Ultrasonic Testing, Film about Russian Ultrasonic Testing Unit Ask 132 and Kalinin NPP, Ultrasonic Testing on mtki.com, Video on Ultrasonic Testing, Karlsruhe University of Applied Sciences, 1.